Hi. Magnetohydrodynamics. It's a long word for a very old principle. The same principle that drives basically all of our electric motors and operates our electric generators. Effectively, when a charged particle, such as an electron, moves, it's associated with an electromagnetic field. And by convention, we use what's called the right-hand rule, which states that if the electron is moving in the direction of my right-hand thumb, the field is considered to be moving in the direction of my right-hand fingers. For you left-handers out there, you're not being excluded because the field doesn't actually rotate or move. It simply has a chirality associated with it, a polarity associated with it, that by convention we consider this to be the standard orientation of the field. And as long as we stay with that convention, that's fine, it's consistent. If we take a wire like this, which is basically an electron tube, and we place it near another wire similar to it and cross the gap with another conductor, following the right-hand rule, the field in this conductor is wrapping this way, the field in this conductor is wrapping this way, and the field in this return conductor is wrapping this way. As a result, these fields are all opposing each other. And as a current were to move through here, as the electrons move through here, they all want to sort of move away from each other. And so these rods, these wires would want to expand away from each other, and this armature would want to move away from the conductive loop. That's basically the principle behind an electric motor. If the armature is free to move and we place current in here, the armature would want to move along the rails. If the rails were round, sort of like bicycle tires, and the armature was connected through an electrical feed, the armature would want to move around within that bicycle wheel pattern and form rotational torque. You'd produce a motor. The field, though, generated by this little loop is extremely weak, and the force is the product of those very weak fields. It's the field of this times the field in this. And therefore, the amount of current that you would have to flow through this loop to produce any meaningful force would have to be thousands of amps. Practically, that's difficult to achieve, and that's why when you look at an electric motor, you will see many wraps of wire, because if I effectively put, say, 1,000 tiny little wires inside of this open tube and ran an amp through each one, I would get the same electrical field outside of the tube as if I ran 1,000 amps through the tube. So in an electric motor, they're sort of recycling their electrons to produce the fields necessary to cause meaningful motion. Nevertheless, it still would require a lot of current to generate any significant force. And so often these motors and generators are augmented by the use of a permanent magnet. A magnet is formed by crystals that have an extreme amount of polarity to them. There's a dissymmetry to the electron distribution. As a consequence, the little particles, the little crystals, are extremely powerful magnets. But before this is formed into a block magnet, the powder that's going to be sintered into this is random. And so there's no net or macroscopic type of magnetic field outside of the sample. After they sinter this into a block, they expose it to an extremely strong electromagnetic pulse, which orients the crystals all in one unidirectional orientation, so that the bulk magnetic field of the magnet is not that dissimilar from the individual magnetic field of the little particles. And that will stay permanently unless you heat the magnet beyond its Curie temperature, which is where the crystals become mobile enough that they can disorient, or you expose it to a very strong contra-magnetic field that can sort of flip the orientation of the crystals. But as long as you don't do those extreme things to the magnet, it's basically forever. If you place a magnet in the same location as the little wire loop that we produced, it's still a magnetic field. And as a result, the force on this armature is the product of not a weak magnetic field times a weak magnetic field, or two low numbers. It's the product of a large number and a small number, and so there's much more force produced by this armature. if you have magnets located in the motor. And that's why when you look at permanent magnet motors or generators, they use these magnets not because the wires are not producing a field, but to augment the field. This process, though, can be inverted. And if you imagine for a second that we've produced motion in this wire because the electrons within it want to move at right angles to this field and at right angles to the current moving through it. If instead what we do is we actually force the armature through a magnetic field, what happens is the electrons within the armature, because they are moving this way, right-hand rule, they produce a magnetic field, and that magnetic field interacts with the permanent magnetic field of the magnet. Therefore, those electrons want to move at right angles to the magnetic field of the magnet and to the direction of motion, and therefore those electrons will be induced to flow along the conductor. Therefore, we generate a current of electrons, and that's how we form a generator. So you can flip it, it's just two different points of view for the same process. The important thing, though, is this doesn't have to be a wire, and that's where magnetohydrodynamics comes into play. Here I have a relatively modest strength N40 magnet, and on either side I have two nickel electrodes. What I'm going to do is I'm going to fill this container with water. Very pure distilled water is a very poor conductor, and as a matter of fact, the very purest waters are often characterized as to their electrical resistance. They're deionized, and the higher the electrical resistance, the purer the water. As a matter of fact, super pure water is actually corrosive because it is lacking in ions, and we can get into that in another video. But nevertheless, we can enhance the conductivity if we add to the water salt, regular sodium chloride, table salt. Salts have a very low ionic bond strength. And so when the positive sodiums and the negative chlorides are exposed to the very polar water molecules, the water molecules will intersperse and cause the positive and the negative ions to separate from each other and flow around inside of the medium in which we've placed them. So if I put that in there, and let me get a little stirrer, these ions can do the same thing that the electrons do. They're much more massive, and there's far fewer of them, and so an ionized water, like salt water or seawater, conducts electricity, but not very well. So we need to use a fairly high voltage to cause any significant current to move between these electrodes. So as the salt is dissolving, I'm going to attach two leads from this power supply to the electrodes. Now, if you've read the book Hunt for Red October, the Russians developed a submarine based on a propulsion system that used magnetohydrodynamics. Kind of interesting because the process does work. That should be saline enough. Now, once that stops flowing, what I'm going to do is I'm going to place a little dye in between the electrodes just so that you can visualize what's going on a little better. And there's a couple of YouTube videos out there that show this. It's kind of a neat little phenomenon. Hopefully it's not flowing too fast right now. Maybe a little bit. Give it a little bit of time. Okay, not much. Now, if I take the power supply and I apply a voltage, what will happen is as the voltage goes up, we start to generate a current, which you'll see over here, and the current will cause the dye to flow. Now if I take my little Q-tip, my little toothpick, and enhance that a little bit, you'll see it's streaming. Kind of neat, huh? Now if I turn the voltage up a little bit higher, you can see the flow is pretty impressive. But if I was working for the Soviets during the development of the submarine, I think I'd probably end up in Siberia if I was proposing to drive a boat with this. Nevertheless, the force that's being generated is proportional to the current, which right now is about 0.3 amps, and to the magnetic field. So what happens if we get a little stronger magnet and a much stronger field? Okay, so now what I've done is I've replaced this apparatus with a new one. And in this case, instead of using an N40 magnet, I'm using an N52 magnet. The number at the end represents the strength of the magnet. This is a much stronger magnet. In addition, you'll notice that the channel width is only half as great. As a result, the current flow is proportional to the contact area of the liquid across the electrodes, but also proportional to the distance that the current has to flow. Making it narrower means that for a given voltage drop, we're going to get more current across here. And as a consequence, we'll get much higher flows from this apparatus, as I'll demonstrate. So when I start to turn up the current here, the voltage, you'll notice that you get pretty darn significant flow. So maybe I won't end up in Siberia quite yet. We're up at 3.5 amps when we were only generating about 0.3 amps before. In addition, you'll notice this foam that's forming here. It's how they discovered, or they were able to locate, the Russian submarine. And this is the hydrolysis of water that occurs when you get over a potential between the electrodes of 1.2 volts. The electrical potential is actually disassociating the hydrogen and the oxygen, and those bubbles are the foam of the hydrogen and oxygen being released. Now, as I said before, a generator and a motor are basically two viewpoints of the same process. And so this process can be inverted, and we can use this process to generate electricity. Let me show you that. All right, now what I've done is I've taken the same salt water, I've placed it in this little burette. What I'm going to do is I'm going to open up the valve and we're going to flow the liquid, and you'll see the voltage here that occurs when we start a flow of the ionic liquid past the magnetic field. Now, as you notice, it's not a lot, but nevertheless, it does show that there is some potential. And the reason that the voltage is so low is simply because we have very little velocity here, and we don't have a very large surface area and a very weak magnet, but 56 millivolts are being generated by this system. In order to get real power out of this, we would have to flow the fluid much faster, and we would want the gap to be much smaller, and the magnetic field, if possible, much stronger. However, the conductivity of ionic liquids is so low that it would be difficult to get a tremendous amount of power unless we could really improve the conductivity. And a better alternative is to get away from the ionic liquids and go to something more like metal, and specifically liquid metal. So we've got a nice apparatus outside, and I'm going to show you what happens when we do that. Okay, because of the low electrical conductance of ionic liquids, what I'm going to do is repeat the demonstration now with a liquid metal. And because I don't like to work with mercury when I can, and certainly not inside, I've decided to use a low melting point metal alloy that will conduct electricity but is substantially safer. This alloy is called Cerolo 136, and it is a sort of a member of a family of what are called eutectic alloys. These are alloys of different low temperature melting metals that, when combined, the individual metals interfere with the crystallization of their neighbors, and so as a result the combination melts at a much lower temperature than the individual metals that are contained within it. Cerolo 136 is a little unusual in that it's one of the few metals that does not contain any gallium and does not contain any cadmium, so it tends to be substantially safer. It's made out of a combination of lead, bismuth, tin, and indium. And what I've done is I've placed some of this in this channel, and we're going to demonstrate how this conducts. Typically this material, when it hardens, looks like pewter, and when it's liquid it looks like liquid solder, and it's frequently used by mold makers to make, say, metal soldiers. It can be used in a machining operation to fixture very delicate components that are otherwise very difficult to hold. And then when you're done with the machining operation, you can simply warm the part a little bit and pop the part out. Because it melts at 136 degrees Fahrenheit, I'm outside simply to allow me to use this heater to bring this large water bath up to above 136 degrees, which you can see on the temperature probe is right now at about 142 degrees, and that's why this is liquid. So now the material in the channel is in contact with the two electrodes like we had before. It's on top of the magnet, and I've got it hooked up to a power supply. And when I apply the current, if I'm not sure you're going to be able to see all of this at the same time, you may want to go through the video a couple of times, or we may repeat this depending on how we edit this. But as I turn on the voltage, the current will rise very quickly, and you'll want to watch what happens to the liquid in the channel as the current goes up. So I'm going to start raising the voltage now. Here we go. See it moving up? I turn it off, and it goes back again. I'll turn it on again. And you can see that the metal, even though it's extremely dense, is able to move up the same hill that the ionic liquid was able to move up. And the current that has been flowing through there is about 15 or 16 amps. As a matter of fact, at the end it was beginning to spark. The capability of moving metal with MHD types of pumps has been applied to cooling nuclear reactors, cooling very difficult to cool high temperature devices where you don't want moving parts. You don't want pumps or pistons or anything that may be damaged by the high temperatures, and you don't want to include them in the fluid loop. And so this is used around the world for cooling purposes. And when we go inside, I'm going to show you how we can use this for a kind of unusual application. Okay, so up to this point, in order to demonstrate some of the forces involved, I've relied on the powerful magnetic field of a permanent magnet. But because, as I explained earlier, there are forces that are generated by the current, if you get enough current, you can actually produce very significant forces. And so what I've done is I've set up a little demonstration here using a power supply to charge a rather large electrolytic capacitor. This is a 4700 microfarad, 450 volt capacitor. And this capacitor is going to be discharged or shorted through what's called a pancake thyristor, or an SCR. These are rather unusual solid-state switches that can handle extremely high voltages, thousands of volts, and can handle tremendous currents, tens of thousands of amps. And the way they work is you effectively charge or allow current to flow through one side, and then there is a small gate that is switched. And the way the gate works is that there is a small bias voltage that I create between the ground of the thyristor and the upper voltage that's produced by the 3 volts from the battery. So effectively, by providing 3 volts above ground to the discharge end of the switch will then open and allow all of the voltage and all of the current from the capacitor to discharge through this loop I have formed between these 2 narrowly spaced conductive rods back down to ground. What we'll do is I'll demonstrate this and show that you can get noticeable forces generated if you develop sufficient amounts of current. And we're going to start charging the capacitor. This is the bolts DC across this capacitor as the power supply is charging it. We'll go to about 50 volts, or thereabouts. And then when I push this button, I will close the switch and will allow the current to go through the 2 conductors. Watch the two parallel conductors. 1, 2, 3. You see they moved apart. The connector at the end was also feeling a force. It wanted to move this way, but it's tethered by the weight of the leads. The current output from this capacitor is proportional to the voltage. The current, the energy is proportional to the square of the voltage, but the current is proportional to the voltage. The forces between these rods, however, is proportional to the square of the current. The field in one interacts with the field in the other. So if I double the field here and I double the field here, I get 4 times the force. So if I charge the capacitor up to, say, 100 volts or twice as high, I get 4 times the force between these two conductive rods. Once we get this up to about 100 volts, then we'll hit the switch and you'll see what the difference is. 1, 2, 3. Substantially different. Now, these are the same forces that are used to operate a railgun. And one of the interesting things is that the current that is flowing through here is actually pretty substantial. It's on the order of thousands of amps, and I'm going to demonstrate exactly what that is with an oscilloscope. Okay, now I've set up the oscilloscope, and what we're doing is we're measuring the voltage across the capacitor, and when we trigger the circuit, we'll show the decay of the voltage across the capacitor as it goes through the dead short. One of the things about these capacitors is that they have a fairly high internal resistance. So it's really the capacitor itself that limits the discharge speed, not these wires. This is significant, as I'll explain in just a second, but what we'll do is bring this up to about 100 volts. And when I fire this on 3, you're going to see a tracing of the voltage that goes across those two. 1, 2, 3. Now, if you see on this scan, the voltage has decayed to about 30% of its initial point. And these are 50 microsecond grids in approximately 100 to 150 microseconds. Now, what that means is that almost all of the energy of the capacitor has been discharged within about 1/6,000th of a second. And that's significant because the two ways that we're going to be going with this information is we're building a very large yoke-style magnet to produce a much higher field than the ones that you've seen in these little test devices, to produce a much more powerful MHD pump, as well as a much more powerful MHD generator that will operate on seawater. In addition, what we're going to be doing is using some of this technology to build a railgun. The principles of a railgun are very easy to understand. I mean, we've just gone through that. But there are two very, very difficult problems that have to be solved with those devices. The first one is that when a railgun fires, the pressures that you see here, which are microscopic based on a few thousand amps, are multiplied thousands of times. And the forces that are pushing the rails apart when a railgun fires are measured in thousands of kilograms. The sliding armature that goes between the two rails has to make almost perfect contact but have almost no resistance. And as you can imagine, that would be extremely difficult to do, because if you have just a little bit too much resistance before any load has been produced, as the projectile or the armature that you're going to be sliding can lock up. And when it does, all the current will flow through it. It will weld in position. It will probably blow up. And if you have enough clearance that it's able to get through, what will happen is under the forces of the discharge, the rails can move microscopically apart. You'll get an air gap. You'll develop arcs and plasma and waste a lot of power and potentially, again, blow up your armature. So one of the techniques that we're going to be using uses the same thing that I demonstrated with the liquid metal. We're going to use a liquid metal sabot to help provide good contact with relatively low machining tolerances. The U.S. military has released information that they were researching this early on, Russian researchers have put out some papers, and the comments are, this looks very promising, but it could be kind of expensive. I don't think that that should be a limitation, at least if the process works, and so we're going to try that. The second aspect of this is that you'll see if you watch a few YouTube programs or YouTubers that are trying to build railguns, they will frequently take a large number of these capacitors, they'll wire them up in parallel, and then they'll use the armature itself as the switch. It's providing the discharge. As I demonstrated, this 4700 microfarad capacitor, which at about 100 volts is storing about 25 joules, will discharge almost all of its power within about a 6,000th of a second. If you imagine a railgun that's, say, about half a meter long, if the initial velocity of the projectile is close to zero and the final terminal velocity is what's ever coming out of the gun, the average speed of the projectile is half that. So if you travel half a meter in 1/6,000th of a second, you're essentially traveling at a speed of roughly 3,000 meters per second on average, and a peak speed of 6,000 meters per second. That's orbital velocity, far higher than any railgun fires. So the problem with discharging these capacitors straight through a dead short is that you end up utilizing all of your power very early on, generally welding your projectile or blowing it up and not getting the power out when you need it. What you need is to use what's called a pulse forming network that essentially gets all the power out of the capacitors that you can, but not any earlier than the projectile leaves the end of the gun. And a pulse forming network introduces inductances to slow down the pulse and tailor it to the length of the time of flight through the rails. In addition, almost all of the YouTubers that have done this, as I said, dead short these electrolytic capacitors through these rails and through their projectile. When they do so, they create tremendous inductive fields, as we've demonstrated here. And those inductive fields, as soon as the voltage drops in the capacitor, will then refeed the capacitor in the opposite polarity. And this sort of refeeding will continue until the capacitor reaches a certain voltage, and then it will again feed back into the field. And this sort of up and down voltage reversal across the capacitor is called ring down. And that ringing in a polarized capacitor is lethal. So it's surprising that any of them survive more than one pulse, but they certainly wouldn't survive many. And that's one of the reasons why you want to use a thyristor or a rectifier to protect the capacitors in the process of building the railgun. So as we move on with this project, we're going to be going in both of these directions, but you can get an idea of some of the principles behind what we're doing. And I'm looking forward to getting the magnet together, and I'm looking forward to getting some real current through the leads. So we'll show you that as soon as those things get a little bit more mature. But I want to thank you very much for watching. I would really appreciate it if you'd subscribe, because it really does help us a lot. In any case, you have a wonderful evening. Good night.